Good morning, guys. I wanted to go over the FRQ grading rubric with you for the two problems I gave you this week. So for the first problem, you have this reaction between nitrogen and fluorine and a lot of different types of thermodynamics aspects. So in order to calculate the value of the standard free energy change, so delta G, Gibbs free energy, the 298 right there, by the way, just means it's standard, and that's what also the little degree symbol means. So the 298 here doesn't really matter too much because we've got 298 everywhere. And remember the equation good honey tastes sweet. It's on your equation sheet on the reference pages. So things to keep in mind is you want to make sure your units are the same magnitude. So enthalpy change is often given in kilojoules per mole. Entropy is often given in joules per mole per Kelvin. So you got to take that into account, and they've changed the joules into kilojoules here before multiplying by the temperature. Okay, so that's the main thing to recognize. Make sure that you are aware of your units, that entropy is often in joules. So multiplying through temperature 298 times negative 0.278 kilojoules per Kelvin per mole, and then subtract that out from negative 264 kilojoules per mole for the enthalpy. Okay, so correct substitution and the correct value, basically using this equation, substituting incorrectly. And I'm not sure if you get the point if you didn't use the right units, so be careful with the units. Okay, so sorry about that. Determine the temperature at which the equilibrium constant is equal to 1. Okay, so if you have Gibbs free energy, you can solve for the equilibrium constant. Okay, so the equilibrium constant and delta G are related by another equation. That's delta G equals minus RT ln K. Okay, so they've substituted in 1 for K, so they have natural logarithm of 1, which is, of course, 0, and so that's a important thing to recognize. Okay, and so so if delta G is 0, then you can solve for the temperature here in this other equation. Okay, so it wouldn't really be possible to solve for it in this particular equation because this entire thing is going to be equal to 0. But if we can plug in 0 for delta G, then we can solve for temperature over here with the good honey tastes sweet equation. Okay, so that's how they've gone through here. Let me know if you have a question about that one. Answer apparently is in Kelvin. You could have done an extra step and put it in Celsius. Calculate the standard enthalpy change that occurs when 0.256 moles of NF3 is formed. So look back up here at the equation. In the equation as written, it's 2 moles of nitrogen trifluoride that's forming, and that's when you get this enthalpy change and this entropy change. Okay, so remember these are these values over here are dependent on how much is involved in your reaction. So this is per mole of reaction as written. So 0.256 moles of NF3 is nearly a tenth. Okay, I guess closer to an eighth of this quantity. So you're going to have about an eighth of this enthalpy. Okay, so put your given amount right here from the problem, and every time 2 moles of NF3 form, that's when you get that enthalpy change, negative 264 kilojoules per mole. Okay, and goodness, 3 points there possible to earn. Okay, so that's I wouldn't have expected that. That should be a straightforward thermochemistry question for everyone. Over here, 6 NF bonds in 2 molecules. Okay, so if you draw out a Lewis structure for NF3, you have 1 nitrogen and 3 fluorine atoms connected together by individual bonds. Okay, so 6 NF bonds would be in 2 molecules. Okay, and then finally here, recognizing that bond energies can be considered to be responsible for the total enthalpy of a reaction. So we got to break apart a triple bond. We got to break apart 3 individual fluorine-fluorine bonds, and then we're going to form 6 nitrogen-fluorine bonds. Okay, so bonds broken, that's positive because that's endothermic. This negative sign is for the exothermic bonds that are forming. Okay, and so the bond energy for breaking apart the nitrogen-nitrogen bond, and the bond energy for breaking apart the 3 fluorine-fluorine bonds, which we don't know, and then subtracting out, that's because it's exothermic, these bond energies. So we're solving for the bond energy of the fluorine-fluorine bond. So you could call it X or 3X. Okay, and then setting that all equal to the enthalpy for the entire reaction. Okay, so all of this equals the enthalpy of the entire reaction, and then we just combine like terms and subtract out, find 141 kilojoules per mole. So 2 points possible for that problem. So there's a little bit of algebra, but just remember, bonds broken is positive, bonds formed is negative. Let's move on to the other question. Okay, so draw a complete Lewis dot diagram for the IF3 molecule. I'm not sure if it really matters, but if it says electron dot diagram rather than Lewis structure, you might consider drawing the actual individual electrons in the bonds. Normally we draw those bonding pairs as lines, but here they have them all drawn out like this. Okay, and a key here is, guys, I was looking over your problems, a lot of you have miscounted the electrons. That should be straightforward, right? The valence electrons, 7 from iodine, 3 times 7 for fluorine, 28 electrons total. So make your bonds, add on the lone pairs, and iodine has 2 of its own lone pairs, and it violates the octet rule. A lot of you guys did not recognize that this was a violation of the octet rule. Okay, and it's T-shaped. It has trigonal bipyramidal parent geometry, but those 2 lone pairs are along the belt where you have bond angles of 120 degrees, and then the fluorines are arranged along the axis and 1 fluorine on the belt. It's T-shaped. Also an issue here that I saw in y'all's problems. Again, counting up the electrons. The reason that the bonds are equivalent is because resonance structures indicate that one single Lewis structure cannot accurately describe the molecule. You have a double bond here and a single bond here, but the real molecule does not have a double bond and a single bond. It's got something between a double bond and a single bond for both bonds. They're identical. The lone pair is going to make this molecule bent. Okay, the bonds are the same length because they are both double bonds. You could say something about resonance structure. It's a dynamic process. Okay, so I'm surprised that, you know, this is maybe an older way to teach that type of thing. Okay, and anyway, it also might be in regards to formal charge, because sulfur can violate the octet rule. So you could draw 2 double bonds in there. Part D. On the basis of your Lewis structure, sp2, okay, you have 3 regions of electrons around the central atom. So you need 3 orbitals that hybridize to give you 3 equal energy orbitals that repel around that central atom. So 1s and 2p, that's 3 orbitals total, 3 regions of electrons that combine to give you sp2 hybrid orbitals. Okay, part E. Notice what's on the axes here, the reaction progress and the potential energy. I had a number of you guys drawing a different type of graph. which was the relative number of collisions and the energy of the collisions. This has nothing to do with collisions. This is not a collisions type of graph. This is a potential energy graph for an exothermic reaction. Okay, they say the reaction is exothermic. So key points to recognize that the system has higher potential energy in the reactants than in the products. Okay, so that's the difference right here. Delta H is negative, it's dropping. We have a little curve here, a bump, that's the activation energy. And the catalyzed version has a lower activation energy, but still starting and ending at the same places. Okay, so don't confuse this with the graph that has the intensity of the collisions versus the relative number of collisions. It's a different type of graph. Okay, so I think that's all for that problem. Let me skip forward one more. No, sorry. So letter F, predict how the ratio of these things would change based on the temperature of the uncatalyzed reaction is increased. Okay, so we have a exothermic reaction and it's uncatalyzed, and we want to know the ratio of the equilibrium pressures. Okay, so equilibrium is not affected by the rate of the reaction. Okay, so increasing the temperature of the reaction will increase the rate. But equilibrium is a different type of thing. However, this is an exothermic reaction. So we could imagine heat being a product. So if heat's a product and we increase heat, which is on the product side, we're stressing the product side, and the system would shift to get rid of some of that extra heat according to Le Chatelier's principle. So we would, if we're at equilibrium and then we increase temperature, the system will shift to reduce the stress. So it's going to shift back to generate more products. So the pressure of SO2 would increase and the pressure of SO3 would decrease. So this ratio would increase. The ratio would increase because the reaction is exothermic, and when the temperature is raised, it shifts to the left. They didn't even mention Le Chatelier's principle, but if you added that in there, that'd be a bonus. According to Le Chatelier's principle, it would shift back to the left. The reaction would shift to the left. How would the presence of a catalyst affect the ratio? Okay, so a catalyst, again, can lower activation energy, but it's going to lower it for the forward and the reverse reaction. Okay, so for the catalyzed version, okay, you would increase the rate of both the forward and the reverse reaction. So a catalyst does not change the equilibrium position, okay, but it does help the forward and the reverse reaction happen as well, but you're still going to reach that same equilibrium position. Catalyst does not affect the two equilibrium ratios, but would increase the rate of the shifting system to the new equilibrium position. Okay, the catalyst does this by providing an alternate path with a lower activation energy. Okay, so a little point here about what catalysts do. They create an alternate path with a lower activation energy, and but they don't affect the values of the two ratios. Okay, equilibrium is dependent, the equilibrium constant, I should say, is dependent on what the reaction is and on temperature, but the presence of a catalyst is not going to affect the equilibrium constant. Temperature would, though. Right? Hope this was helpful.